Okay, everyone, welcome back. So today we'll continue studying properties of vector fields and their integrals. You probably saw on the B courses that we have decided to cancel the last quiz because indeed probably it's too much of the testing. So once we're done with the material, we'll just switch to reviews. So probably most of the next week will be review sessions and office hours by demand. Yeah. Are there any questions on this? Yes, time frame for the final will be 24 hours, and you need to submit it within a 4-hour window. That is correct. I know that some people individually are asking about sort of different times because they have conflicts with other finals, and on a case-by-case basis, I grant those exceptions. It will start on 9 a.m. on Friday. Yeah. I'll make a separate announcement. I haven't set it up yet via grade school. So I think it will be 9 a.m. Friday till 9 a.m. Saturday. All right. Yeah, so if the final is what it's more it will contain 3 times more material than the quiz, roughly. So you should think about maybe 11, 12 problems, maybe 1 problem for the extra credit. In total, will be 4 hours. So usually final is 3 hours, but because you need to do the submission of papers and all the circumstances around it, I think with the 4-hour window is the best time frame. Wasn't there an extra credit problem for the midterm? Yeah, I mean for the recent midterm, yes, there was an extra credit problem. I think, well, I mean, Emma is still grading it, so as far as I remember, there was a and B part, and then B was for extra credit. Was it not the case? Okay, I see. So I need to remind it for myself. So grade scope. For the midterm, I'm sorry. No. For the midterm, yeah. So for the midterm, there was no extra credit problem. I was talking about quiz 4. Yeah, that's right. That is correct. Yes, I misread the first sentence. So the final will contain the extra credit problem. Yeah, so this way, so we will be done like in about a week plus a little bit. Then the next semester will start, right? So it's in late August. Okay, so we should continue. So we talked about in the end about line integrals of vector fields. So we discussed line integrals of functions or scalar fields and line integrals of vector fields. And the way this integral is defined, that we take a vector field along the curve, right, and then we multiply it. They take the dot product with the unit tangent vector at that point along the curve, and then you just integrate over the curve. So since the unit tangent vector is equal to the derivative in the direction so it's r prime over absolute value r prime, then we can simplify this and write. So if curve C goes from A to B, then explicitly in terms of parameterizations, it's equal to the following integral. So we take dot product of f of r with the derivative of r, right? And then that gives you the integral. So let's look at an example. So let's take one of those vector fields that we had studied before. It's the so-called twisted cubic. And say that t varies between 0 and 1. So, for the vector field, let's pick some function. Vector function with coordinates of x, y, y, z, and x, z. Right, so this way, so this is f, and then r, we can just, we can read it off from here. So it's x, y, and z, right? So it has t squared and t cubed, and then we'll need derivative of r. So r prime will be equal to 1, 2t, 3t squared. And we need parameterization for the function f, right? So xy is t cubed, yz is t to the 5th, and xz is t to the 6th. So if you're looking at the formula above, integral over c of f dr, you can write it like this, is equal to, so it's integral from 0 to 1, and then we calculate the dot product, so it will be, well, xz at to the 4th, that's right, thank you. Yes, 6, there is no 6. Yeah. And so integral from 0 to 1, and that's equal to t cubed times 1 plus t to the 5th times 2t plus t to the 4th times 3t squared dt. And that gives you t cubed plus 2t to the 6 plus 3t to the 6. Or it's t to the 4 over 4 plus 2 7ths. Oh, let's actually get this. It's 5 7ths, right? So 5 7ths to the 6. From 0 to 1, which is 1/4 plus 5 7ths, or it's what? It's 20. Oh, sorry. Yeah, it's 27, 28. Yeah, this is the answer. Yeah. So now, of course, again, so you probably have seen this integral before in context of some physics course. And even the notation for the vector field is somehow suggestive, right? So if F is the force, and then we integrate the force over the path like this, which physical quantity are we going to get this way? So in terms of dimension, right? So it's force multiplied by distance. Yeah, that's right. This is work. Only now because it's no, it's over the path. You have to you actually have to integrate, right? So work like maybe I should put mechanical work. Mechanical work. So I'm sure in high school or whatever, you solve the problem when you have a block on the surface and then say you're acting it with a constant force, let's say F, which is directed with angle alpha to the horizon, right? And then if block has mass m, and then you move it, by distance L, then the mechanical work which is required is equal to F times mg, right, times cosine of alpha. So I'm pretty sure you've seen you've all seen this formula. So now we have but pretty much let's get back to the curve here. We have precisely the same situation over here, only that the angle and the force changes, right? So that's why we actually need to integrate. So it would still be true for small displacement, right? Like well, L. I'm sorry, I forgot L. So I get getting not fresh again. Multiplied by L. Yeah. So never mind. MG is irrelevant. Sorry. Yes, FL cosine theta. Yes, FL cosine theta. What was before was not correct. Right. So if angle theta is 0, then you'll get the maximum work. If it's the higher you pull, the smaller the option of the work. So remember we did this calculation when we looked at pedal strokes of bicycle. Right? We set up a similar integral. Yeah. So yeah, so that's the easy physics interpretation of what the integral over the vector field over the curve is. Again, and another fact from physics which you probably are aware of. So if the force is conservative, or in terms of our language in this course, if the vector field is gradient, right, then what happens? So what was so special about work in conservative fields like gravity or electric field? Yeah, so work done by closed loop is 0. That is correct. And if loop is open, then what? So yeah, so Alex is saying that so we draw some three-dimensional coordinates. And so there's a path like that from point A to point B. And then there's a vector field here. Everywhere, right? So you are integrating it over this curve C, right? And then we know that the vector field F is gradient, which means that there exists a function phi such that F is equal to nabla phi. But then The question is, what is the integral over C of f dr? FDR sounds like President FDR. So yeah, so what Alex was saying, if you have a closed loop, you know, and then you come back again, then the work on the closed loop is equal to 0. So let's say this loop is gamma, work on over gamma is equal to 0. And now let's see what we have. We have an open loop. So our point starts its motion from point A, goes like this, and then arrives at point B. And we know that okay, so let me reformulate the question in terms of school physics. So if you have a ball of mass m at height h, and then you dropped it down, right? So what was the work of forces of the gravity force? Well, what is the value of the work which was done by gravity on the ball? mgh, right? So and mgh is also a formula for what? So work is equal to mgh, and it also the answer for which point? Yeah. So what kind of energies we have in mechanics? We have kinetic energy, energy of motion, right? And we have what? Potential energy, of course, right? So as you should probably know, the potential energy is up to the choice of the basis. So let's say there's a potential energy, let's put V. There's the energy V here, and there's some energy V0 at height 0. So the work of these forces is equal to the difference, right? Is equal to the difference between the potential energies, right? So in this case, the work exerted by gravity will be negative, right? So technically we should put a minus mgh, right? And it's equal to just gonna write it here. So W is equal to minus mgh. Gh is equal to potential energy at level 0 minus potential energy at level h. And so because the difference here is h. So now how this story will generalize, well, to our question, right? So that is what? This will translate into integral of the force vector times dr over c, right? Because see, this is force, and this is the displacement, right? It's well, delta r. In this case, it's constant, right? And it's equal to a difference of potentials, right? And then here, so I think we discussed when we talk about gravity, right? So the force is equal to the negative gradient of the potential. So potential energy here. So yes, the same notation. A negative here, and that's why we have this minus sign. Okay. So that's what we should expect. We should expect the difference of potentials between endpoint and the beginning of the journey. So let's do this calculation here. So let f will be gradient phi. Let's calculate the integral of f over the curve. So let's pick a standard parameterization for curve C, which is a piecewise smooth, continuously differentiable function from AB to R. Well, let me do the example for R3, but of course it works for any. Actually, let's do the whole thing for Rn. So then the answer will be equal to the integral from A to B f of r of t dot r prime of t dt, right? And that's equal to remember that f is a gradient, right? So it's a integral from A to B, and then we have df so f is a gradient, so this is equal to gradient phi. So let's write components of the gradient, right? So it will be d phi over dx times x prime plus d phi over dy. Yeah, I'll write the example for R3, it's okay. Plus phi over z times z prime dt. So yes, so here R prime has components of x prime, y prime, and z prime, right? And the by chain rule, this can be combined as into time derivative, t derivative of phi of r of t. And so that's literally what the chain rule says. Right, so it's equal to the integral of a total derivative, d over dt phi of r of t. So it's equal to phi of b minus phi of a. So it's the difference between the potential function and the potential function at the endpoints. I forgot there. Let's not put minus here. There is no minus. Yeah. That's right. So it's the difference between the potentials. Yeah. So yeah, we can call this function potential. Okay. Good. So this is just some facts that you knew, only expressed in this more universal language. So then what was said earlier about integral of a closed loop. So now let's assume that a loop is closed. Which means that phi of A is equal to phi of B. Like in this example, so this point is A and B at the same time. Well, then, as you can see from the formula, the answer, the integral of over the closed loop is equal to 0. Right? Simply because you have identities and you have 0 in the right-hand side. So this has this fact has the following consequences, meaning that the answer for the integral does not depend on the choice of the path, right? So you have, say, we take a closed loop, and then you can break this loop into two segments. Say this is point A, this is point B, and you can integrate over this branch, or you can integrate over that branch. And let's call this path gamma 1 and this path gamma 2. So if the vector field is gradient, then integral over gamma 1 of FDR is equal to integral over gamma 2 of FDR. Because, well, simply you can, the proof of this fact goes as follows. So let's format as a proposition. So claim let f be equal to an amplifier for some phi, and there's this configuration here that we have a loop, then then this integrals are equal, right? So this can be shown as follows. So you can move one integral to the left. So you have integral of gamma 1 minus integral over gamma 2 of FDR. And now remember what I told you about the orientation. So if you flip the direction of integration in gamma 1, right, so to here, you will have you can call this loop gamma 1 inverse, right? So then these two integrals, they combine into integral over gamma 1 and then connected to it gamma 2 inverse. So this inverse sign simply means that you go in opposite direction. And you can call this curve C. And the answer is 0 by the previous observation. Yeah. Questions? That's right. Okay, but turns out that you can say more than that. You can say that so in a gradient vector field, so if the field is gradient, then integral does not depend, integral between 2 points, line integral between 2 points of such vector field does not depend on choice of the path. But in fact, there is no opposite statement. So if the integral does not depend on choice of the path, then okay, so never mind. So this has been put right. So again, the two statements that, just to recap, the two statements are equivalent. That independence on the path is equivalent to having integral of a closed loop to be equal to 0. Okay. So this was proven. And now let's talk a bit more about connectedness. Connectedness and simply connectedness. And we'll look at some interesting examples. Yeah. So what is a connected set? So example, let me just draw some examples, then you'll see what. So this is a connected set. This is a connected set. This is a connected set. Right. So a set is connected if you can connect every 2 points by a curve or by a path that belongs to the set. And so a set is connected. And for the purposes of the discussion, let's say it's a subset of Euclidean space. If any 2 points of the set can be joined by a path which belongs to the set. Yeah, and when we say path, it's the same as curve, yeah, or yes. Again, topology. What does WSS stand for? Where is WSS? Oh, connectedness. I'm sorry. I tried to write connectedness. Yeah, it's a property of a set. Yeah, sorry for that. Yeah, and so this set is also connected. Right, but now there's something different about this set, right? We have, well, two kinds of paths, right? We can go around this hole like this, or we can go around the hole like that, but it's still connected, right? The definition does not constrain any, it does not put any restrictions on the number of those paths. In fact, in both cases, the number is infinite. It just, well, we'll talk about this momentarily. So, but you can see clearly that the second set is fundamentally different from the first one, right? And then finally, the third set is also connected, right? You can put you can go like this in the spiral, and you can connect any 2 points. Okay, so then the following statement about we can make the following theorem about connected sets. Right, so if F is a vector field, which is continuous on a connected open set. And sometimes such sets are called domains. Right, and if the integral of f over C is independent on the path, on the path that is contained in the set, let's call the set D, right? So, and then if the integral, if the integral over the path C is independent on the choice of this path, then f is conservative, right? So then there exists a function phi such that f is equal to gradient phi. Right, so there's an opposite statement which sounds which is also true. So if this if set is connected and the integral does not depend on choice of the path, then the field is gradient, and the yeah, so there exists a potential for which the field is gradient. Question: a connected set divided the domain superscript into multiple connected sets That's super. I don't understand the question. So just the name. So domain is an open connected set. We'll talk about simply connected in a moment. Oh, this is a subset. Right. So C is a curve and it's contained in D. Like this red curve is a set of points that's contained in. So yeah, so this is C, right? This is D. And it's like a Venn diagram. You have, subset. Okay. So okay, maybe this question will get weird. Okay. So let's prove this statement. Oh, I'm getting to the bottom of the page. Let's see, I should be able to copy it. Not all. Do it one more time. So it doesn't allow me to. Okay, I'm gonna rewrite on top. So what we're going to do, we will construct this function by hand, right? So we will discover this potential. Okay, I'm going to rewrite the theorem in a short sort of symbolic way. Right, so let this be a curve in D, and then the integral of f dr over C does not depend on the choice of C. Meaning that we have a set, right? And then we have 2 points, and then the integral like this and integral like that are the same, right? So there's a C1 here and then C2 there. And then here integral over C1 of f is equal to integral over C2 of f. Yeah. Okay. So let me give you another plot here. So let's start from some point. With coordinates A and B. Right. And then, so our goal is to define the potential. We need to finish the theorem. So hence, there exists a potential, so function phi of x, such that f is the gradient of phi. So our goal is to define the potential at every point, say point xy, right? So what we can do here, we can So yes, let's see. Yes, and let's say it's a two-dimensional. For the sake of the calculation, it's a two-dimensional example. So we want to construct this function phi of x, y everywhere on the set D. Right. So so since this line integral is independent on the path, right? So it doesn't matter which way we'll go to this, from which path we'll choose to go from one point to another. So we'll do the following. So we'll go horizontally here to some point with coordinates x1, y, and then we'll go to, well, we're gonna go to point AB over some smooth path like that. Right, so this we'll call C1, and then this part will be called C2. Right, so and then this point XY will be in some epsilon neighborhood, so it will be close to it will be close to XY. You'll see in a second why this is easier. So this disk goes. So since D is open, right, it's a domain, which means that every point is interior, right? So we can it belongs to the set together with a small disk, right? So you can pick a disk of some small radius, maybe epsilon, such that, and then let's integrate. Let's pick a path that goes horizontally over here, and then we just connect it down to the point to the point AB. Right. So we want to find the. So let's construct the function. Let's just define it. So by definition, this function will be integral from our point AB to point XY. So again, point AB is chosen arbitrarily of f ds dr. Right, and we, as a path, right, we choose it to be, as we drew, integral over C1 FDR plus integral over C2 FDR. Right, so since the integral doesn't depend on choice of the path, we are free to pick any one we like. Right, so this path is equal to integral from AB to point x1, y, and the integral over C2, right, is equal to, well, let's just write it like this for now. Okay. So then let's find the explicit parameterization of F. So let's say F has components P and Q, and it's a two-dimensional vector field. And so yeah, so we can write it here, and now so as you see from the picture, the choice of the path, since the integral does not depend on the choice of the path, in particular, it does not depend on this first integral, it does not depend on x, right? It only depends on x1, right? So therefore, we can let's take derivative from both sides over x. We have d over dx of phi of xy. Then this integral, the first integral, does not depend on x, so it's equal to 0 plus d over dx of integral over C2 p dx plus q dy. And so we talked last time that you can write the integral of a vector function like that over the vector field like this. Okay, so but on the curve C2 here, so it is parallel to the x-axis, right? So therefore here dy is equal to 0, right? So this is equal to 0, and well, because everything is continuous, and we can swap the order of integration and differentiation, so it's equal to integral over C2 dp over dx dx. Right, and this is the total derivative, which is you can actually write it in more detail here. So it's integral of x from x1 to x. Right, so if you do this calculation, you'll get that's right. So you get p of x y minus p of x1 y. Okay. Something is not right. Hold on. I take derivative. I get p. Oh, I'm sorry. Yes, it's not quite right. It's not quite right. Should be p. Give me a second. Yeah. So I did something wrong. I'm sorry. Yeah. So like I'm going to start over next line. Right. So we now let's integrate that. So x here, right? So we take a derivative over x, which is the limit of integration. Yeah. So I'm going to continue here. So it's equal to d over dx, right? Integral from x1 to x, right? And then here it's p of some t comma y dt, right? So because this curve is parameterized by a parameter t here, right? And t varies between 0 and say between x1 and x. Right, so t is between x1 and x. So when we do this integral, yeah, that's right. So like this, right? But we know that there's a formula from single variable calculus. When you have an integral like this, and then it's a function of the upper limit of integration, then the answer simply is equal to p of x, p of xy, right? So x1 here is a constant. It does not, so the integral does not depend on that. Okay, so we have shown that phi prime x is equal to p. And analogously, you can show that phi prime of y is equal to q. Right, so to do that, you'll need to combine the similar procedure. Well, now you'll need to integrate over a path that looks like this. Well, first you'll need to go down to some point here. With coordinates, well, too much stuff here. go down on this red path. Let's call it C4, to the point with coordinates x, comma, y1, and then do like this along path C3. And repeat the calculations. Right, so you have the following thing. You have d over dy of phi of xy will be equal to d over dy of integral from y1 to y of q of x comma t dt, and that will be equal to q of xy. And so this proves the theorem because, because remember P and Q are components of the vector field F, so therefore you can write them as phi x comma phi y, or it's a nabla phi. Okay. So therefore F is the conservative vector field. Now the value of this choice of the function, choice of the point A, B was arbitrary, right? And then you can make the value of the function of the potential. You can put the potential to arbitrary value at that point, right? So that will tell you that the choice of the potential is up to you, right? It doesn't matter where you pick the potential energy. It does not affect any calculations. Okay, any questions? So you see here, the proof is a little bit more complicated than usual, but the theorem is pretty strong, right? It says that whenever the integral does not depend on the choice of the path, it enforces the field to be conservative. It has to be conservative. There is no way out. Okay. Good. Let's take a small break, and then we'll continue with more from vector calculus in several minutes. Oh yeah, so we already started. We started working on 16.3 since I forgot to put a number. So everything from the independence of the path of the integral, and for the conservative vector field, that was 16.3. The connectedness is also 16.3. I mean, I'll give you some more stuff than in the book, but so this theorem is in the book. Yes. So this is theorem 4. This is theorem 4 from 16.3. Okay, let's make a quick break. Okay, let's get back to vector calculus. Any questions? Yeah. So maybe another comment on the choice of the path. So since every smooth path can be sort of approximated by this kind of zigzag path. So you can always sort of, the calculus is the science of small, right? Infinitesimal. So then that's how we can calculate integrals, for example, right? That's how we calculate lengths of curves, etc., areas. So here, if you have a path between 2 points, it can always be broken into segments of horizontal and vertical lines, and you could apply the same logic here. So you would integrate over a horizontal path, and here dy will be 0, and then you will integrate over vertical path, and then dx will be 0. So you can sort of move from one point to another by going over those staircases. That's a good picture to have in mind. Okay. Right. So next statement is about, so say we are given some function, a vector function, vector field f, and then we can ask ourselves whether it's conservative or not. So what are the conditions on vector functions or on those p and q, right? So that the given field is conservative. So say there's a field in 2 dimensions, and you're just given 2 functions of x and y. Question: how to know for sure if the field is conservative? Well, the answer can be quickly understood from these 2 formulae, right? So if it's conservative, then there exists a function phi, which we call potential, such that phi x is equal to p and phi y is equal to q. Now, we assume that everything is differentiable here, so let's take another derivative. Well, now let's do them in a different order. So let's calculate phi x y, that will be equal to py, and phi yx, that's equal to qx. Right, so I take derivative of first equation over y, and derivative of second equation over x. So we have these 2 equations, right? And because of continuity, we expect that the mixed derivatives are equal to each other. So that brings us to the condition that dp over dy is equal to dq over dx. So here's another theorem. So vector field f with components p and q is conservative or gradient if for every point in this domain, so it's conservative on D, which is a subset of R2, right? So it's conservative if for every x, the following condition is satisfied. Right, so okay, so that's the statement in one direction. So let's look at an example. So you take vector field f, which is equal to 3 plus 2xy, I, right? So plus x squared minus 3y squared times j. Right, so this is p of xy, this is q of xy. So let's check. So py is equal to 2x, and qx is equal to also 2x. So it checks out, they're equal to each other. So the answer is yes. Right, the field F is conservative. If this condition fails, it's not conservative. Okay. So in other words, so if field is conservative, yes, so then these conditions should be satisfied. Now, how about the opposite condition? Sort of, how about the statement in opposite direction? So can we find a condition on the vector field and on the domain D such that vector field will be forced to be conservative? Okay, and this is where the notion of simply connected set comes in. So remember on the previous, at the bottom of the previous page, we had two examples. We have like a blob like this, which is a topological disk, right? Which is like it looks like a different disk, and we had let me draw something different. So we have a set with two holes. So that's the set. Okay. So they're both connected, right? Because clearly you can connect every 2 points with each other by a path that belongs to the set. But there is something fundamentally different for the second set. So namely, there's a path that can go like this, and there's a path that can go like that. There's a path that can go like this. What is there anything else? What else can you do? You can go, yeah, but you can go around, So I drew 3 paths which look different. So can you imagine any other path that would look yet different from those 3? Figure 8, yeah, excellent. Yeah, so we can do figure 8. So let's say, yeah, you can go like this and then come back. And in fact, you can wind around any of those holes as many times as you like. And technically, every such path will be different, right? So when we say different, we mean that they are so-called topologically different. So you cannot continuously deform one path to another. Continuously meaning that without breaking. And so if every path, if every closed path here can be continuously contracted to a point like this, as it is possible here, then the set is called simply connected. If it's not possible, then it's not simply connected. Simply connected. So D is simply connected if any closed path in D can be continuously contracted to a point. like this, right? So like you can, so what it amounts to here is that it encircles in the interior of the path, it encircles only points are inside of the set. Right? So for example, here, this is not the case, right? So every loop around those holes will contain points from those holes which are technically not in the set. And therefore, so if you cannot continuously pull it through. So otherwise set is not simply connected. So the set on the right is an example of a non-simply connected set, and they have interest in topology. So I recommend all of you to take class Math 142, the Intro to Algebraic Topology, which explores this notion further. Yeah. So let's look at an example. Sort of to understand this non-simply connectedness, and then this is a classical example from complex analysis. And so the vector field is this. It's x over x squared plus y squared and minus y over x squared plus y squared. So I mentioned here and there complex numbers. So as a complex number, you can write this as a complex weighted function, which is 1 over z, right? It's a side note. So you can write z as x plus iy, and then 1 over z, you should write it as, well, it's z conjugate divided by absolute value of z squared. Which you can write as x minus iy divided by x squared plus y squared, or it's, you can break it into real and imaginary parts, x squared plus y squared minus iy times x squared plus y squared. So that gives you a real, so the real and imaginary part of this complex valued function can be identified with components of this vector field. Yeah. So you can see here that it's defined everywhere except the origin. And so for set D, we should take a set of R2 minus 0. And because this function is not continuous as x and y approach 0, right? It diverges. And let's integrate over a circle of unit radius this vector field. So 0 is a singularity, you have to remove it. Right, and then there's a circle of radius 1. It's minus 1, and this is also 1. Let's integrate. So the circle S, we could call it S1, right? F dr. And so let's do the integral. We talked about this, right? So the we drew the shape of this vector field yesterday in the first class about vector fields. So it exactly gives you the tangent, right? So over here. So vector field with components. Actually, no, I'm sorry. And then never mind. Yeah, sort of. Would you gonna write the integral? Yeah. So, right. So that's equal to. So let's parameterize the circle. X is equal to cosine t. Y is equal to sine t. Then f will be given by cosine t minus sine t. And so conveniently, everything in denominator cancels off, right? Then r, vector function r, is equal to, right? So this is r, is cosine t sine t. This is what the derivative r prime is equal to minus sine t cosine t, and so integral will be equal to integral from 0 to 2 pi f dot r prime dt, which is equal to integral from 0 to 2 pi of so it's at minus 2 sine. This way it will cancel. Hold on, give me a second. I thought I got this for. Should be the other way around, right? So, yeah, f should be like this. I'm just trying to understand where's the mistake. Yeah, so if f is this, then this would work. What's the, yeah? So then the but it should be the complex number. Okay, I can probably look it up and tell it more. So hold on. So the derivation from complex analysis should be, yeah. So it should work like this, right? So you have integral dz over z, right, and then we write z as e to the I theta, right? And then the integral will be equal to integral. So then dz is equal to I e to the I theta d theta, or it's I times z d theta, right? So then the integral is equal to I z d theta over z, which is equal to I times z cancels, and it's integral from 0 to 2 pi is equal to I times 2 pi if integral over this S1. So that's how it's done in complex analysis. So now let's see what's the yeah. So what needs to be done is yes. Let's take the field that we have, right? So let's take it with a minus. Yeah, I think that yes. So this one, this field indeed integrates to 0. Yeah. So I think I know what a mistake is, but so yeah. Let's take a different function. So right, so different field. Let's call it g. Right. So g of xy. Let's call it minus y of x squared plus y squared, and x of x squared plus y squared. So this field indeed was, as we discussed before, will go along like this. Right. So it's always, it will be tangential. It will go along the tangent lines to the circle, right? And the integral over g r prime dt from 0 to 2 pi, right? In this case will be equal to, so if you use the parameterization, so then g of g is a function of t, will have components negative sine t, cosine t, and then that gives you, of course, so r prime is equal to this function, right? And g is equal to that. So we take the dot product, and it gets integral from 0 to 2 pi times sine squared t plus cosine squared t dt, yeah, which is equal to 2 pi. That's right. So the answer is not equal to 0, right? Albeit it's a closed, it's a closed circle, right? Yeah, so this vector field, as we know, this vector field is not gradient. I mean, I told you this when you haven't proved this. Yes, so this vector field is not gradient, and also the set is not simply connected, right? Because there's a hole here which you need to take out. So yeah, and this factor is used in complex analysis. So whenever we have a complex function, which you can rewrite as a real function of two variables, rather two real functions of two variables. One is the real part, one is the imaginary part. Whenever this function behaves as like this, as 1 over z, so you can integrate around the small circle, small circle that contains this singularity, and then integral over the circle will be equal to 2 pi multiplied by pi. If you try to write it in real variables, in real components, you'll get this. Yeah. Now the sort of the illustration is that although the function 1 over z, you can think of 1 over z as a gradient still, right? So because if you integrate 1 over z, you get a log, right? So if you formally say that, okay, as derivative d over dz of log z is equal to 1 over z, and then you can ask yourself, well, why is it that the if this function is a total derivative, why is it the case that the integral over the closed loop is not equal to 0, right? And the answer for this is because the set is not simply connected, right? Because this point, the origin, does not belong to the set, and therefore even although the function is a total derivative, albeit in a complex sense, the answer is not equal to 0. So the entire thing will be, we should look at the derivation that is, so the form, you should look at the bottom, right? So yeah, so the entire thing is this. So we looked at two functions, two vector fields. One is x minus y, so the answer here is equal to 0, and the other one is this is minus yx. Yeah, sure. So in complex analysis, this is called the residue. Residue of function 1 over z. So you would divide it by 2 pi I, and then so residue of the function 1 over z is equal to 1. Questions? Yeah. So to summarize, let's write this theorem here. Is that so? If you have a vector field on an open, simply connected set, and the conditions with the derivative are satisfied, then f is conservative. Right. So let f be equal to p and q. So defined on a simply connected open set D. Then also suppose that py is equal to qx. Then so for every point in D, so for every x, y in D. So remember, it's an open set, so therefore it contains every point of the set contains a small disk, right? Therefore, this happens. This is true in some disk. So then f is conservative. Oh, O/W is otherwise. Right? It's one of those standard shorthands. You know, there's this. This is otherwise. What WO stands for? W/O. That's without, right? And then W with a slash. Yeah, that's right. So, no. And correct, yes, and OW is otherwise. Good. Okay. Great. So there will be a lot of problems. I put a lot of problems for practice. I think we covered most of it. Not most of it here. Okay. Okay, our next story is 16.4, Green's theorem. See, I'm writing greens with green color, so it should go well. And also it's a more general statement would be Stokes' theorem. Now, the sort of it's the following statement. So say you have a set D as a subset of R2 with a boundary, right? So although D is open, but you can find a closure of D, right? So we have a say open disk, you can find you find a closed disk just by including the boundary. Same can be done with any set like this. So let's say C is the counterclockwise oriented boundary, right? And well, because of its nature, it will be a curve into dimension. So the following thing is jinx in a row. So the idea behind Green's theorem and Stokes' theorem in general is to connect the two-dimensional integral over set D with a line integral over the boundary. And this is what it says. It says that double integral over the disk over the set D of the following combination. So Qx minus Py dA dx dy is equal to the line integral over C. And here it's assumed that the boundary is positively oriented. So it's counterclockwise is equal to P dx plus Q dy. And sometimes, because it's a closed thing, people write a circle here. So it's a circular integral, which in LaTeX has a symbol \O int. Yeah. Now, you probably see the similarity here. We have seen these two guys before, right? Over here. So turns out that if the field is conservative, right, then this left-hand side is identically 0, and therefore the solution should be the right-hand side. Which is not surprising. That's exactly what we talked about in the theorem, right? The theorem says that if this is true, then the field is conservative, and the answer does not depend on the choice of the path. And if you have a closed path, like we have here, so the circle and integral itself, it designates the closed path, then the answer must be 0. So if you wish, the Green's theorem shows you the deviation from that. It's like, what if it's not the case, right? So what if this vector field is not gradient, and you still want to calculate the integral over the boundary? What will it be equal to, right? And the answer is this. Yeah. So that's what the theorem says. So we're not going to give you so the proof of the theorem goes in 2 steps. So first we prove it for a rectangle or for some simple region, and then well, you can, as I mentioned earlier, you can chop the boundary into those sort of staircase-like shapes, staircase-shaped piecewise regions, and then you would, well, let me maybe, I'm gonna illustrate this claim by, see, this is my set, I want to cut it horizontally and vertically into small stripes like that. And yeah, so we can draw the boundary. So the boundary will be approximated by this piecewise path. Like this. And well, so yeah, so it goes counterclockwise like this. So now let's do the following. Let's take a rectangle, which I highlight here. I hope it's still legible. So if you integrate over this rectangle counterclockwise, and then we integrate over the rectangle that stands next to it, different color. And then you can see here the integral should go counterclockwise like that. Then integrals over this interface will cancel off. Right? So whenever we have integrals from rectangles, so say you have one rectangle and then you adjoint to it another rectangle and yet another rectangle. So these counter integrals like that will involve integration over those interfaces. In one case, you integrate this way. In the other case, you integrate that way. Same here. So therefore, integrals from those interfaces will cancel. And what will remain is integral over the boundary. And I hope this picture sort of is self-explanatory. So you have a, you can chop this region into those long rectangles. You can either do it horizontally, you can do it vertically, it doesn't matter. And when you adjoin those rectangles together, the only thing that is left is the boundary integral. So if you prove the theorem for a rectangle, you will have proven it for the region of general shape. Question from Daniel: wait, so why does it have to go counter? Well, it's a convention. So if it would go clockwise, the answer, there will be a minus sign here. Yeah, we'll see it from the proof. It's same reason why when you have polar coordinates, you count angles counterclockwise. Okay, so is this topological argument clear? So when you put rectangles together and agree that you integrate around each of them, well, in the same direction, clockwise or counterclockwise, let's say it's counterclockwise, the only stuff remains is the boundary integral. So now let's prove this theorem for a rectangle. So suppose D is a rectangle. And then we just need to calculate each of the so say we have points, what is not them? X0, Y0, X0, Y1. No, it should be X1, Y0. X1, Y0, X0, Y1, and X1, Y1. Right, so we'll do it. Let's do the horizontal integral. Well, let's notice pieces of path C1, C2, C3, C4. So integral over C1 of P. So here Y changes, Y is constant, and what changes is X, right? So it's, well, I'll write like this: integral C1 P dx, right, is equal to integral from X0 to X1 P of T over Y0 dt. Right, and the same is true for Same is true for all others, right? You can write single integral for each of those paths, right? So, oh, I'm sorry. Here goes the. One sec, I need to reinitiate. Oh, come on, now it wouldn't start. There we go. Right, and then let's write the one for C3. If we have just enough time to finish that, so, and then integral over. And since dy is equal to 0, it suffices to just look at p here, right? So an integral over C3, part C3 of p dx, right, is equal to integral from, well, with the minus sign, right, integral over from x0 to
Hi everyone. Somehow there was a problem with my desktop again, and now it should be fine. So, well, I think we should do the proof anyway next time. So, let me get to 1 second.
Thanks everyone. Yeah, so I'm not sure how did you find out, but anyhow, maybe you know someone who knows someone. Yeah, it is the birthday. Ah, okay. Yeah, so it was the message. Anyhow, so I think, yeah, okay, well, let's continue to tomorrow. So basically the idea of the proof was to, well, let me just quickly show it here. So when you integrate over C1, and so basically, yeah, so when I write it like this, double integral of d over dy over p will reduce to, say, here C1 equals to C3, right? So that equals to integral from x0 to x1, integral from y0 to y1, right? dp over dy dx dy. And because it's a total derivative of y, we can write it as integral from x0 to x1 b of x, yeah, so p of x comma y0 minus, or rather y1 minus p of x comma y0 dx, right? And this is what it's minus integral over c3, and this is a minus integral over c1. And similarly, you can show that double integral over d over dx of q will give you contributions c2 and c3, c4, excuse me. Right, so if you combine them together, you need to add this and then add those to get the formula with the right sign. So you'll get the integral of p dx plus q dy is equal to double integral qx minus py over d. So yeah, I will review that tomorrow. And so this way you're going to get integral over here just by difference between the integrals on the boundaries. Okay, great. So that's it for today, guys. Thanks for coming, and we'll see you tomorrow. Bye.